or shows neither. So.
The seat's right in the front if you like.
I'm really sure but it seems like these sessions are just video listening to and whatever it was. Figure out the moment just as long as I speak. Are you trying to sort of include the audio into the stream? But for the people that are watching,
I also am fortunate enough to chair the BCS Awards Committee, where this year we gave the Lovelace Award to Andrew Blake. First, some housekeeping. So this lecture is being filmed, and it will go on the BCS web page soon. It's also being live streamed to BCS members, so please, mobile phones off, no laptops on, that sort of thing. It just interferes with what's going on. The Lovelace Medal is awarded each year to individuals who've made outstanding contribution to the understanding of advancement of computer science or engineering. The recipients are given the opportunity to give a public lecture in fabulous Royal Society, and the turn this year is Andrew Blake. Before we give him the award, I'd like to introduce two people who will introduce Andrew Blake properly. The first is Professor Sir Tim O'Shea, who's Principal and Vice-Chancellor of the University of Edinburgh. And the second is Chris Bishop, Director of Microsoft Research Cambridge and Professor at Edinburgh. Thank you.
Good evening, ladies and gentlemen. It's an honour to be invited to introduce the 2016 British Computer Society Lovelace Medal recipient, Professor Andrew Blake. Andrew has very good links with the University of Edinburgh, so as its principal, I'm particularly pleased to do that. Before I talk about Andrew, I do want to say a few words about Ada, Countess of Lovelace first. Ada was an inspiring person who lived in the 19th century. She was a mathematician and writer and is chiefly known for her analysis of Charles Babbage's analytical engine. Ada had been asked to translate Babbage's lecture notes about his invention from French to English, and she saw that the machine had greater potential than pure calculation alone. In her notes augmenting her translation, she included an algorithm for the analytical engine to compute Bernoulli numbers. So she was a great scientist, had an ability to think about computing in the sense that we think about computing, and I'm very glad that my own university marks International Ada Lovelace Day with various computing-related activities. And now to tonight's Lovelace Lecture, lecturer, Professor Andrew Blake. He's a very worthy winner, and I'm delighted that the British Computer Society has recognised him for his outstanding contributions to the understanding and advancement of computer vision in particular and computing in general. Andrew is the research director of the Alan Turing Institute, the UK's National Institute for Data Science, and former managing director of Microsoft Research, Cambridge. After his undergraduate degree at Cambridge, he was working for Ferranti, where he realized that he was engaged in computer vision, and then he did the obvious sensible thing, which is he moved to the University of Edinburgh to do a PhD in artificial intelligence. And it's still, by the way, if most of you look a bit past it, but if you are a person who suddenly finds you're interested in machine learning or computer vision or such, then you should try to get into the University of Edinburgh. I do encourage you. Andrew is extremely able and brilliant, and so, of course, he got into the University of Edinburgh to do a PhD supervised by Donald Mickey. Donald's a tremendous track record and did wonderful things in terms of leadership of what Donald called machine intelligence at the University of Edinburgh, and he is a link back to Bletchley Park. Donald Mickey worked with Alan Turing, and he was one of the people who worked there on code breaking. Andrew, in his PhD, looked at parallel computation in low-level vision. It was a very successful doctorate. He then stayed on as a lecturer in computer science with us, and then in 1987 he moved to Oxford. He joined Microsoft in 1999 as a senior researcher and went on to become a Microsoft Distinguished Scientist and Lab Director before standing down in October 2015 to found the Turing Institute. And there's a really nice set of connections. You know, he's supervised by Donald, who worked with Alan Turing, and then Andrew goes on and works on the foundation of the Turing Institute. He's retained his links with the University of Edinburgh, returning to our School of Informatics as visiting professor in 2006 and receiving an honorary degree of Doctor of Science from us in 2013. And the University of Edinburgh is one of the 5 key partners, along with Oxford, Cambridge, UCL and Warwick, in the Alan Turing Institute. Andrew's lots of recent achievements: the Royal Academy of Engineering Silver Medal in 2006, the Institute of Engineering and Technology's Mountbatten Medal in 2007, and with colleagues at Microsoft Research, the Royal Academy of Engineering's McRobert Award 2011 for their contribution to Microsoft Kinect human motion capture, and also very nice continuity from his PhD work. Andrew was elected Fellow of the Royal Academy of Engineering in 1998, elected Fellow of the Royal Society that we're in 2005, and a Fellow of the Institute of Electrical and Electronics Engineers in 2008. Elected to the Council of the Royal Society in 2010 and to the Board of EPSRC in 2012. So that's an amazing series of distinctions, and he's an amazingly bright, and he combines it with a really nice, easygoing manner. So if you don't know him and you come and have a talk with him after his lecture, you will find he's not at all an arrogant person, and you could get arrogant with all those distinctions, but a really very charming, grounded person. I will now hand you over to another charming, grounded person, Professor Chris Bishop. And Chris, as well as doing the Microsoft thing, is also a professor of the University of Edinburgh and has just moments ago become a Fellow of the Royal Society. So please welcome Chris.
Well, thank you very much, Tim. Perhaps I could just begin by saying heartfelt congratulations to my good friend and long-standing colleague, Andrew Blake, on winning the Lovelace Medal. Well done. I thought I'd say a few brief words about Andrew's time at Microsoft Research in Cambridge. Microsoft Research in Cambridge was the first lab that Microsoft set up outside of the USA. This year we celebrate our 20th anniversary. Andrew and I were both quite early hires into the lab. Andrew's job was to set up a computer vision group. My job was to set up a machine learning group. But we had a very early conversation, and I think we had a good deal of foresight, it seems, because we realized that machine learning, one of the biggest applications of machine learning, was going to be in computer vision. And equally, computer vision was about to be revolutionized by machine learning. And so we did something a little bit unusual. Instead of setting up competitive groups, we decided to work together. And we set up a single group called the Machine Learning and Perception Group. And I'll give you an example of one of the things which Andrew encouraged the group to work on. It's the problem of object recognition, just recognizing everyday objects in visual scenes. Not because we plan to ship this in the next release of Microsoft Office, but just because it was a deep scientific problem, yet one which, if solved, would surely have lots of applications, and maybe Microsoft could benefit from some of them. Well, fast forward a few years, and Microsoft's Xbox division, the games division that makes the Xbox console, had decided to do a very brave thing. Instead of releasing a new console much faster than the previous version, essentially building on Moore's law, that would be the obvious thing to do, it did something much riskier and much more adventurous. It decided to create a revolutionary kind of interface. Instead of these sort of joystick controllers, it would track the human body in real time, and your body would become the controller for the computer games. So they built the wonderful hardware, they wrote the software, everything was all set to go, and there was a little snag, which is it didn't actually work. And it didn't actually work because the tracking process was too brittle. It failed too often. And they're a bit stumped because they'd made a major bet, really a very major bet on this technology. And so they turned to Microsoft Research Cambridge and to Andrew Blake and his colleagues and asked for help. And Andrew and his colleagues realized that what they needed to do was to leverage some of this apparently very different technology, this object recognition technology that they'd been working on for a number of years. And to cut a long story short, it solved the tracking problem. Kinect shipped in time for what the Americans call the holiday season, so it was a great success. As a result of that, Andrew and colleagues won the McRobert Award, the gold medal of the Royal Academy of Engineering. The work was also published. It received a top prize in computer vision, an enormous number of citations, and also Kinect went into the Guinness Book of Records as the fastest selling piece of consumer electronics of all time, beating the two previous record holders, which were the iPhone and the iPad. So you can imagine a degree of satisfaction at that moment. Well, Andrew became the director of Microsoft Research Cambridge in 2010. And in his 5 years or so as lab director, he made many other important scientific contributions to the direction of the lab. But I'll just finish by mentioning one of his contributions, which is of a rather non-scientific nature, but nevertheless has had a profound and lasting impact on the lab, which is that he took us to a new building, a building right in the centre of town. We'd sort of been on the outskirts, a beautiful building designed specifically for conducting research, and incidentally inspired in part by the wonderful Informatics Forum at the University of Edinburgh, has a marvellous atrium running the whole height of the building. And not only did he design this wonderful building, but he equipped it with the most beautiful artwork. And Andrew is somebody who is not only an incredibly talented scientist, but has impeccable taste for art as well. And in fact, his parting gift to the lab when he moved on to set up the Alan Turing Institute was to give us this wonderful grand piano, which sits in the foot of that atrium. And at least one of our staff members is a former professional piano player, so occasionally we have this wonderful music wafting up the atrium. So really, Andrew, just on behalf of really all of your former colleagues at Microsoft Research Cambridge, huge congratulations once again. And for the important part of the evening now, we look forward to listening to your lecture.
Thank you, Chris and Tim. So now it gives me great pleasure to give Andrew Blake his award, the Lovelace Medal.
Wow.
And And now here's his lecture, Machines That Learn to See.
Well, it's a great pleasure to be here and talk to you all tonight. Actually, Chris has given quite a lot of my lecture, so that's good because it means we can get to the drinks just a little bit earlier. But he said something about telling you about Connect, but he was cutting a long story short. Well, I'm not going to cut the long story short. You're going to get the whole thing. So, yes, it's been a fascinating time, I think, in what we can now, again, with a clear conscience, call artificial intelligence. So my PhD was indeed in artificial intelligence at a time when it wasn't terribly fashionable. And so, we've all been very patient. And now one can, with pride, say, yes, I work in artificial intelligence. And a very important part of artificial intelligence is learning. And so I want to talk about how learning also has become so important in making machines that learn to see. As you've already heard, I'm now at the Alan Turing Institute, but there was this whole string of institutions before that you've heard all about, the University of Oxford in between. I didn't stretch back quite as far as Ferranti that Sir Tim mentioned, but sure enough, that was there even before Edinburgh. So before I launch into talking about artificial intelligence, I suppose it might be interesting to see what Ada Lovelace had to say about it. And in fact, in her write-up of that Sir Tim mentioned of the work of Babbage, she expressed a certain amount of scepticism about artificial intelligence. The analytical engine, which we were hearing about, that could compute things, nonetheless, she said, had no pretensions whatever to originate anything. It can only do the things that we know how to order it to perform. So it's not a mind, perhaps, in some sense, but just a slavish machine. On the other hand, if she was trying to make artificial intelligence work, here is what she was using to try and make it work. So it's sort of a little bit more elaborate than a sewing machine, perhaps, but perhaps not altogether surprising that artificial intelligence didn't quite work on that. Nonetheless, nowadays what we're seeing is artificial intelligence and one of its principal components, which is machine learning, powering so many of our largest companies. And here are many that you know, Amazon, Google, Facebook, and so on. The other two that you might not recognize are Yandex at the bottom, the bottom there, which is the Russian Google, and Baidu, which is the Chinese Google. And all of these multi-hundred billion dollar companies are really running on machine learning. Machine learning has come out of the lab and become a principal driver of businesses. Big businesses and also many more smaller businesses that I don't have space to put on the slide. So machine learning is a very important part of the vision story. But before I tell you some of the details about how vision works, I suppose we should just check that vision really does work. And so I just wanted to talk about a few of the machines and devices that people have built that we are beginning to take for granted that run with machine vision inside. The cameras you all use have a lot more intelligence in them than one might think, and I'm going to come back to this a little bit later. The advances that powered the ability to recognize faces in the camera and help you frame up a good shot came out of the research lab and into the device amazingly quickly. The research was only 2000 or so, and within 2 or 3 years, everybody had this on their cameras. Another thing which we all enjoy, which perhaps we don't think of as being artificial intelligence or machine vision, is panorama stitching. And so actually, if you take a kind of, you could imagine, and perhaps even remember, when you had to take photographs very carefully, like sort of eating sweet corn, kind of, in order and going down the scene. in order to get the pictures to fit together and make a panorama. Nowadays, we don't have to worry about that. You can go out and take a lot of pictures, and a kind of jigsaw puzzle is solved that creates a panorama that all joins up. But the components, the pieces of the jigsaw, don't have any indentations. So what do you have to do to get them all to join up? Well, actually, you have to do quite a lot of artificial intelligence work to kind of go halfway to recognizing the elements of the scene. Perhaps not so far as to say that that's a house and that's a tree, but still to recognize when an element is repeated in one photograph and appears in another photograph. So there's a surprising amount of analysis going on quietly under the hood to fit all those pictures together. Another great example, an area where machine vision has made a lot of difference, is in medicine, and I'll come back to this later, but one application of machine vision in medicine is in putting together images of your body taken on different occasions. So if you return to the clinic perhaps 6 months after your original scan, and you have another scan is done, of course you're in a slightly different position, and you may be fatter or thinner than when you last came, and so when you want to compare one image with the other, they're not going to fit. However, with computer vision, using technology rather like the panorama stitching technology, that is, recognizing fragments of the image that get repeated the first time and then 6 months later, you can take the second image and stretch it until it fits the first image, and now the clinician can use that to make a very direct comparison between the state of your body across visits. Another lovely application which at some point just started to work reliably is eye tracking. Before the invention of visual eye trackers, and here is the eye tracker, if I can. This is a regular laptop with an eye tracker bolted onto it, which is itself a machine with cameras in it and special illumination. Until the invention of these machines, if you wanted to do experiments on detecting where people are looking under various circumstances, you had to do rather ghastly things where you would sit inside a cube with a set of what they call Helmholtz coils, great big 1 meter radius, 1 meter diameter copper wire coils, and to excite, in order to get a signal from these coils, you would wear contact lenses on your eyes with thin wires coming out of them. It doesn't really sound very tolerable, does it? But if no one else, the experimenter, the psychological experimenter using this equipment was always willing to put on the contact lenses and be tracked. But now we don't have to do this. Now we have optical devices like this one with the cameras and the infrared inside. It's infrared illumination so that you don't notice that it's operating. And so you see what happens, that you can actually follow someone in this amount of detail, that you can see how their eyes are moving as they read a text. This is a wonderful technology which I think will find many other uses. Perhaps one day, this is the hope of the people who build these trackers, will become part of our computer user interface so that the computer can work out what you're attending to and react more appropriately. Another fascinating application, which is rather recent, from University of Aberdeen, is with psychological testing. And so what you see here is a schizophrenic patient and a control, both invited to look at various stimuli. The first one is a Lissajous figure, where a dot is traveling in a systematic fashion following a pattern on the screen, and another is a kind of free attention task, where the subject is simply invited to look at a picture and choose what to attend to, and you see how strikingly different the patterns are for the schizophrenic patient and the control. So this is rather exciting because it suggests that there might be some independent instrument that could estimate the presence of mental illness. Another thing which really works, and this is of course going to be a very big one for us, is driverless vehicles or autonomous vehicles. I want to show you a video of how they looked in 2005 when I was lucky enough to go round the Myra test track near Bedford in the converted Mercedes, and here is what it was doing. You'll see them, here we are. and there's a squealing of brakes, and the Mercedes grinds to a halt, having detected the pedestrian on the skateboard. When I was there, they did it with real pedestrians, and the life of the research assistant, the poor research assistant, was saved for the 10th time that day. Then we went round the nearby town, Nuneaton, and they decoupled the system from the brakes and switched it, connected it instead to a buzzer. And so what happened was, as you went around the town, the system would buzz when it saw a pedestrian, and every 2 minutes or so it would buzz when it saw a lamppost or a railing or other random objects. So, as well, we didn't connect the system up to the brakes because that would have been jamming the brakes on at random about every 2 minutes. So that was what they had to do to get from 2005 to 2013, which was the point at which they actually fitted these systems to the cars. So now various companies, high-end cars, including Mercedes, you buy their cars, they will do various automatic things. Things like steering cruise control that follows the curve of the road rather than going straight, and will occasionally stop for a pedestrian much faster than you can. I also went in their experimental car 10 years later, and this time it's doing something rather more sophisticated. It's looking at the pedestrians, not just to see if they're in the way, but also to see what they're attending to. So if you look carefully, you'll see two pedestrians are about to appear, one of which looks at the driver and the other doesn't. The guy in the brown sweater there is looking at the driver, and the one in the green over there is not. And the question is, can the car tell the difference? And here you see it's telling the difference, so it doesn't bother to stop. And this guy sailing across the road, he can see the car now, but that was a bit late, and the car stops in time. So, ever more sophisticated technology. This is still experimental, but for sure this will be on our cars before long. So Tim mentioned that I started out in Ferranti, and actually the very first thing that I did in computer vision before I even realized it was computer vision was working out how to help air vehicles, helicopters navigate using vision. And here is my first patent. It looks relatively unsophisticated. Two cameras pointing downwards. I guess any of us could have drawn that. There was a little bit more detail in the patent about how to compare the signals coming from the two cameras, and that by detecting the delay in the signal in one camera relative to the other, you should get a good idea of the speed of the helicopter. But now you'll be thinking, what happens if the helicopter goes sideways, which they can, and perhaps things won't work quite so well. Anyway, we worked on that, and as Sir Tim says, I realized, well, this is computer vision. I could do this in a university, and I did. Now, 35 years later, all kinds of things are happening in this area. In the UK, we're actually rather strong in autonomous vehicles. Universities of Oxford and Cambridge both have very strong groups doing the research on this. In Oxford, they also have had a company for a few years, Oxbotica, with experimental cars in Milton Keynes and Greenwich. In Cambridge, a startup, 5AI, has just been launched, and I've joined its advisory board. And of course, these companies have a lot of hot competition from around the world, from companies great and small. I think it's going to be a very exciting time for autonomous vehicles. So I wanted to convince you up to this point that computer vision really does work, and that there is something to explain. When I was working in Edinburgh on my thesis, it took about a day to process an image. Now we're processing images at many tens per second, and that is an enormous change. Actually, the kind of fulcrum of that change was around the late 90s, and that was what made me think of going to Microsoft. It seemed like this was this had moved on from being speculative research to being an area where you might actually build machines with computer vision systems inside them. Very early on in the history of computer vision, in MIT, people were thinking about this. This was an artificial intelligence lab. MIT, along with Stanford and Edinburgh, were really the three pioneering labs in artificial intelligence. And they were working on other matters, particularly on on logic and automating logic, but they thought as a corollary of their work on logic, perhaps they could also solve computer vision. And so they set a task for some students. This was July 1966. They thought perhaps they could do some analysis of simple objects, children's bricks and cylinders and so on, and they thought that would be quite hard and would probably take the whole of July. And so they left until August the much harder problem of looking at less regular objects like batteries and cigarette packs which had patterning on them and so on. So they'd allowed 2 months to solve computer vision, and you see we're still here, 60 years later, is it? Hang on, I can't do the sum. 50 years later, still trying to solve this. So it turns out that seeing is very hard for a machine to do. I want to give you an idea of why it might be so hard. So here is a hand as seen through the eye of a computer. It's a TV camera that's connected up to the computer. It could be a webcam nowadays. And what you might like to program the computer to do is to see the outline of the hand. That would help with the task that Chris mentioned of using the body to control the computer and having the computer understand the movement of the body. So really what you'd like is for the computer to be able to infer an outline like this one. And because we know that that is the outline of the hand, but the question is, what does the computer see when you present it with a signal like this? And what the computer sees is much more like this. And I promise you, this was not deliberately done badly. This is a kind of fair crack using signal processing and image processing techniques to pull out the interesting parts of this image, the parts that might be outlines of things. And you see, you get the outline of the hand, it's in there somewhere, but there's a lot of other stuff. There's all the clutter on the desk, and there are various markings on the hand, shadows and so on, which are not part of the outline. And the trouble is, we have such incredible computers in our crania that are effortlessly filtering out all this irrelevant stuff, that it's hard to overlook just how difficult objectively it is to pull out the irrelevant detail and retain the detail that matters. And I suppose one of the things that came out of that MIT work, why it didn't work in 2 months, is because we learnt as a field that telling a computer what to do in the way that Ada Lovelace talked about was just not going to work for things like computer vision. And the same is true of understanding speech and understanding language. No one has managed to write down a set of instructions directly in the form, I mean, of course, you know, programming computers, that is what you do. You write down a list of instructions in the form of a program, but nobody managed to do that for these kind of perceptual tasks like speech and vision. And they did try, but it was just too hard. So in 1998, my colleague Michael Izzard, who now works for Google in Silicon Valley, and I wrote this book where we were beginning to explore what you would do if you couldn't program the computer to see these things. What would you do? And so we began to explore teaching the computer about the natural world and getting the computer actually to learn. So, for example, we told the computer a little bit about what a hand was, but then we showed the computer many hands and hands in many positions to try and get the computer to understand and model the variability of the position of the hand. So this idea of using learning because you can't program perception has become a very important idea, and around the time we wrote this book, a number of labs around the world were thinking about that. Another thing that's difficult about the task is the ambiguity of natural scenes. So, you know, we see a certain amount of ambiguity here. We're not quite sure. As I've covered up the original image, it's now a bit harder to tell which of those contours is the real one. And this is something well known to psychologists, that our brains are very able to deal with complex ambiguities. Now, those of you that studied psychology at university, if there are any of you, or perhaps if you've read popular books about perception, you may have seen this image. So you should keep quiet while the rest of you try and work out what this is. And I suspect that some of you will see, don't shout out the answer, some of you will see what this object is, and others of you may be looking at it puzzled. Anybody, you'll be amongst friends, you could indicate if you can't see what's in the image. Anybody can't see? Not sure what it is? Yeah, a few people. And if I say dog, Dalmatian even, that might make it easier. There are probably some people for whom saying Dalmatian was enough. There's the snout, Dalmatian, there's its ear, there's a foreleg, and there's a rear leg, I guess, and it's on a sort of spotty, leaf-coloured forest floor. And if you still can't see it, I'm afraid there's nothing I can do for you except go on to the next image and give you another chance. So probably fewer people have seen this one. I wonder, some people will probably immediately see something in the image, don't say the answer. Others will be looking at it in a sort of puzzled fashion, wondering what on earth is this? Is it a scrambled egg? What is it exactly? For those, I will first of all say, well, there's a bearded preacher in the picture. And that will probably help some of you. Anybody got it because I said bearded preacher? Yeah, a bit of nodding. Some people still not got it, a bit cross because they can't see what it is. Is that true? Yes, there's some cross people in the audience. I'll give you one more hint, which I'll show you a smaller version, which sometimes helps people to see it a bit more easily. Okay, some revelations there. Some people still stamping their feet. Okay, bearded preacher, there's an eye, that's a mouth. This bit is a beard. Anybody left naive? Of course, now, those of you that couldn't see it before, now you've seen it, you can't go backwards. The hypothesis has been sort of instantiated against the evidence, and you will never be naive again. And you probably could be shown this picture in a month's time, and you'll still recognise it. Well, just one last riff on this idea of ambiguity. I want to show you this movie of, well, what is it a movie of? Let's see. It's blurred, isn't it? Which is a bit frustrating. A blurry movie of somebody in the office. What are they doing? Put down the cell phones, put on the headphones, typing on the computer, using the mouse. All looks pretty normal. And you managed to do all that despite the kind of poor quality of the information. So well done for that. Let's look at the original version that's a little bit sharper. So he's talking on his shoe and put on his tin cans, typing on the, using the mouse, is really a stapler, and the computer is an inverted waste paper basket. So, the point of this is that we are very good at tolerating ambiguity. When I showed you the first image, which had a lot of ambiguity because of the blur, you still managed to make sense of it. The fact that that turned out to be not quite right is still, I would say, pretty creditable. I think you should be proud of your vision systems for doing well, but also your vision systems were capable of assimilating further information when it came in later to break the ambiguity, and you, as it were, revised the hypothesis. So almost like there's a scientist in your head exploring the image as if it was material in the science lab, trying various hypotheses to see what would best explain what's in the scene, and finally able to adjust that hypothesis as better and better information comes in. Richard Gregory, the famous psychologist, put it very well. He believed that perception was exactly this thing of testing hypotheses against the evidence that is out there in the scene. Richard Gregory is very well known for his many illusions. He loved to play these tricks on his audience, showing them how their vision systems could oscillate between hypotheses and be fooled by deceptive kinds of evidence. There's the very famous cafe wall illusion, which is a pattern on a particular cafe in Bristol at the foot of St Michael's Hill, if you happen to be there. And the interesting thing about it is that, and now what you see here will depend where you're sitting, because further back you'll get a different illusion than further forward. I'm not quite sure who will see what, but some of you will see oblique lines in the image. And the oblique lines probably not very stable. Sometimes they lean one way, sometimes they lean the other way. Are you getting that? Nod your heads if a lot of the nodding is coming from around the middle of the room, so maybe that's where it works best. And but actually the lines in that picture are all straight. And the slant is a kind of illusion as a result of the vision system trying to make sense of what's in the scene. Another of his illusions, this is in some ways even more vivid. Here is a mask of Charlie Chaplin rotating in front of you, and as it rotates, you see the backside, you know you must be seeing a concave. I mean, it must be, mustn't it? It's a mask, so it must be concave. But it's actually quite hard to see that. Some of you probably will see the concave face, but I suspect that more of you will see a convex face, because after all, faces are convex, kind of rotating in the wrong direction. Is that right? And so there's some interesting interplay here between your prior knowledge about faces, which happens to be particularly strong prior knowledge, because you really very rarely saw concave faces, that interplay between your prior knowledge and the evidence that is in front of you. And it's so strong that it even overwhelms what you consciously know about a face and gives you this percept. So this is where we are. We want to make vision systems work, and there seem to be two very important principles. One is that we need to deal with ambiguity. The brain is very good at dealing with visual ambiguity, and it computes, and so for us making artificial intelligence, it seems like a good idea would be to use probability, which is a mathematical language specifically designed to cope with probability, with uncertainty. You use it when you're betting on the horses because you're not sure which horse will win, and so you talk about the odds of such and such a horse winning, and that is a kind of intuitive way of applying probability to an uncertain situation. And the other thing that we've seen is that we've heard rather is that attempting to program direct instructions to a computer to see just isn't going to work, and so it will have to be done by learning. So this is what I want to explore in the rest of the lecture. So we're going to think about probabilistic mechanisms of learning and reasoning. And I want to spend the lecture contrasting two different ways of doing this. The first way is empirical detection, black box detectors they're sometimes called, where large amounts of data, big data, for example, all the images that Google stores on the web, there's a lot of it, could all be used in principle to teach some computational machine how to discriminate various things. For example, how to name objects, rather, as Chris was mentioning earlier on. And building a black box, making adjustments to various knobs and so on inside the box in order to get the best result is in some sense going very directly for the result that you want. It optimizes predictive power. You'll twiddle the knobs until you get the very best prediction out of this box. What's to stop you? You have no other criteria you need to meet, so you'll twiddle the knobs until the very best prediction is made. And so this is seems like a very sensible approach to solving these problems of identifying things and classification. And it's become very influential in the recent years, and actually these things tend to come in waves. I'll come back to why it has become so interesting recently. The alternative that I want to talk about is generative modeling, which is a more, I suppose you could say it's a more roundabout way of doing things. Instead of going directly for a machine that will do the classification, instead the first step is to kind of describe what's out in the scene. And this is done in probabilistic language, talking about the objects that may appear in the scene and the features that they have and the variability of those features captured by probability. And this is in many ways an attractive thing to do because there are methods which take that description of the scene and automatically invert it into something rather like the black box, something which will actually analyze the scene. So getting the analysis for free, having only had to do the description, is a sort of a remarkable boon, if you like, something which has happened once or twice in artificial intelligence, most noticeably with logic programming, which is another non-probabilistic style of programming, where again, you just simply have to describe something, and then for free, as it were, you get a recognizer that matches that description. So generative modeling is very attractive because of this the kind of stepwise description that you build up, which seems so very rational, that captures what's happening in the scene. And so when these generative models are used for classification, you get the benefit also that they come with an explanation, not just the decision that they made, but why they made that decision, how they came to the decision. Whereas the black boxes, as their name suggests, not capable of doing that. You can't really look inside the black box and learn anything very much. So I want to talk about these two paradigms, and this is mostly what I'm going to do for the rest of the lecture. So we have these two paradigms. Which one is going to be the winner? Well, let me begin by talking a bit about the empirical detectors, the black boxes. I'll have a bit of mathematical notation from time to time on my slides. If you like that, enjoy it. If you don't, ignore it. The narrative will still work. So supposing we have an image which we'll call I, this is a pile of pixels, and a state which we'll call X, and the state is the interpretation of the scene. So the state might be the presence or absence of a face, like the camera has to do, or it might be something to do with the position of the human body, describing all the angles of all of those joints for the configuration of the human body in the scene. And so the job of the empirical detector is to eat the image I, pass it through the black box, and pop out at the other end a description X of what is happening in the scene. And if we want to say this in probability speak, because after all we were clear that we wanted to use probabilities because of all of that ambiguity, then we think about conditional probabilities, the probability of a particular configuration of the body X given the input image I. And these black boxes, as I said before, are learned from big data, exploiting the fact that we can really collect a lot of data now, often labeled data, that is to say with some caption or something similar saying what that data is. And so there's a big opportunity to learn there. And as I mentioned earlier, the cameras that we have that recognize faces were one of the first fruits of this way of doing things. They were actually a bit of a shock when they came out. At least the science was a bit of a shock. When it came out in 2000, people were trying to do this kind of thing in very different ways. I was working on recognizing things in successive frames of a video, and it seemed obvious that to recognize what is happening now, you really ought to exploit what happened just a fraction of a second ago, because surely the two things are not going to be very different. That seemed absolutely obvious. And one of the shocking things that happened with this new technology was that the face detection worked so well that you didn't even need to know what happened a fraction of a second ago. Nobody bothered when they saw how well this worked with linking successive instants. How did they do it? Well, they would collect a lot of data. Here you see on the left a lot of examples of faces, and on the right a lot of examples of near misses of faces. It turns out that you need positive and negative examples, and if the negative examples are near misses, that's particularly useful. And then you define a set of patterns, sort of elementary patterns that you then look for in these examples. And I mean, I've only shown 5 patterns here, but in reality, you would use hundreds of thousands of patterns initially, and then refine those down to perhaps a few thousand. And as a result of that, the scientific advance was made that enabled people to locate the faces, and as I say, it passed into technology very, very soon. Chris mentioned the work that we did in the lab a little bit later on, where we kind of pushed that a little bit further. So this was partly done in the Microsoft Research Lab, partly in the Chipola Lab in the University of Cambridge, where we now could recognize maybe 20 different things. Some of these are things, some of them are stuff. Water is stuff, it's kind of texture. The cow is a thing, it's a discrete object. And we could deal with maybe 20 different categories and recognize them with reliability around 90 to 95%. So that was a very significant advance. But of course, soon people were not content with that, and they upped the ante a little bit further, and at some point, a really rather difficult challenge was posed by researchers at Princeton and Stanford universities. They made a collection of 1,000 different kinds of image. You see there the word net there is telling you the themes: world, people, child, home, room, and so on. Those are the different themes of the images. And for each theme, like room, there would be 1,000 images. So 1,000 times 1,000, 1,000,000 images all together, all with their identities. And then what this group did was they issued a challenge to the artificial intelligence community to solve this problem, the problem of identifying reliably what was in each image. And people tried many different things with the kind of wisdom of the day, and they did quite well. They got so that they could recognize which category the image was in, and this is now 1,000 categories, so it's a much harder task. And they could do it with about 75% accuracy. So not the 90-something% that we had with just 20 classes, but 75% or so. And at that point, people started trying harder and harder to get that number up, and trying new tricks and new approaches, and they just could not shift that number, and the whole enterprise stalled for a while until something completely new came along. And one of the inventors of what have come to be called deep neural networks challenged the vision community to use deep neural networks to solve this challenge. So what is a deep neural network? Well, here it is. It's a series of boxes. It's one of these black box classifiers that consists of a sequence of components. And what you see here doesn't really matter too much what the boxes are, but each one takes a signal in from the left and spits out an altered signal on the right, and the box itself does the altering. So you see the images would come in on the left here and go through several stages of alteration, becoming sometimes bigger, sometimes smaller, until finally they're spat out on the right-hand side, a long string of zeros, but with a 1 somewhere. And the 1 corresponds to the class that has been recognized as the image. So if the 137th spot in that string of 1,000 corresponds to car, let's say, then what you'd expect is 136 zeros and then a 1 and then the rest zeros, meaning that that car has been recognized. So it turns out that building these networks, building them so deep, that is with so many stages, and being brave enough to do it, which somehow, and having the computing resources to do it, made a huge difference. And so when we look at the graph of how performance in recognizing these classes progressed, here is the level when the neural network started to be used, rather high, almost 30% error, and getting steadily better year by year. And actually the latest from last year is that now this task is being solved just a little bit better than humans can do it. So I think it's fair to say, as far as this task is concerned anyway, that machines have now reached the level of humans in this particular task. And now people have gone on to do even more with these kinds of ideas. Actually, instead of associating a single word with a picture, trying to infer the caption. And so here you can see a computer trying to work out what's happening in this picture. And it's got several ideas. You see, could be a purple camera with a woman, or it could be a woman holding a camera in a crowd, could be a woman holding a cat. That's ambiguity again. So, there's the putative cat, I suppose. But at some point, after weighing the evidence, the computer decides, no, it is a woman holding a camera in a crowd. And so this is really quite a level of achievement. There's lots more to do. This is perhaps, you might argue, as Fei-Fei Li, the professor from Stanford who issued the challenge, did argue in her TED talk that at last computers have got to the level of performance that you might expect of a 3-year-old. And so she stood up at TED and said, well, we've done 3-year-olds on to 13, which was, maybe a little bit of overconfidence there, but you see what she means. So the black box detectors, they really are incredibly powerful and working very well. Now I want to consider a different kind of problem, another one that we worked on at Microsoft. Supposing you wanted to separate the object from the background in this image, and your experience is limited, well, to this image. Nobody is offering you that database of 1 million images, 1,000 llamas in perhaps many different scenes. This is Machu Picchu, as I'm sure you instantly realized. And so the technique of using big data, because for that is what it is, to train these black boxes really is going to be rather difficult to apply here. So what might one do instead to separate foreground from background? So we have very little training data. In fact, in this case, it's sort of the extreme that there's only one image. What on earth are we going to do? Well, this is where it turns out that the opposite tack is rather powerful. We talked about the empirical detectors, where you begin with the image I, you infer what's happening in the image, which we code up as X. You do that probabilistically, that gives you the conditional probability. And instead, we're going to do this generative modeling, which works in a strangely backward fashion. So what you think about is a kind of simulator. Supposing I tell you what's in the scene. Supposing I were to tell you that there is a face in the middle of the picture, and it's about 1/3 of the size of the picture, something like that. Then I could have a go at synthesizing a picture with that face in it. And of course I might get the wrong face. It might be Chris instead of Tim. So I might have to have several goes at this before I get anything like the scene that you've actually seen. And so you could think of this as repeatedly drawing from the probability distribution, probability of I given X. I fix this description, face in the middle of the scene, and I keep drawing at random more simulated images that have that face in the scene. And at this point, we wheel on Thomas Bayes and his famous formula. Thomas Bayes, another very strong connection with Edinburgh, both historical and the fact that they're now building the Thomas Bayes building. I'm not quite sure why it's taken you 300 years to build the Thomas Bayes, but anyway, I'm very, very pleased that it's coming. And now the job is to use the magic formula of Bayes to invert this relation. Because remember, what we really want to do is to take the image I and talk about the interpretations of that image given the image I. So inverting this turns out to be doable with Bayes' formula, and then one might do something like maximize this function with respect to X to find the most probable interpretation of the image. Now, this has arisen from work in artificial intelligence, but it turns out it's not only researchers in artificial intelligence that have spotted this trick. And if you go to the Whitechapel Gallery very soon, you'll see a fabulous exhibition of the work of Edoardo Paolozzi. And one of his exhibits is called, fortuitously enough, the conditional probability machine. And he has 24 different images that are, and he was actually, this is not a coincidence, he was actually fascinated with artificial intelligence, with Turing in particular. He has a whole set of images which we have a copy in the Alan Turing Institute, and there's another copy in the Royal Academy of Engineering just next door here, of kind of variations on a theme of Alan Turing. He was obviously fascinated with this idea of artificial intelligence. And here are some of the images, sort of artistic renderings of what might be going on in your brain as you kind of play with conditional probability. And if you're too late for the Whitechapel Gallery, then you can go instead to Tottenham Court Road Tube Station, where they've just restored his beautiful mosaics. And there are many images rather like this, only a lot more colourful actually, on this theme. Okay, back to the job in hand. Analysis by synthesis using generative models, this business of making a kind of simulator of images and then reversing that simulator. So how do we do this? Well, we have to unpack the image a little bit and think of it as a pile of pixels. So capital N here will be 1 million, for example, if you have a 1 megapixel image. And here are all the pixels comprising the image. Here are a set of states, the 1 million of these as well, and these are binary, just zeros or 1. 1 means that pixel belongs to the object. 0 means it belongs to the background. And so the next job in the generative model, in building the generative model, is to kind of take account of the colors that are present in the scene. And actually, if I flip back to there, you'll recall that the scene, you know, the colour palette for the foreground is not very well differentiated from the colour palette for the background. So that really is going to make life difficult. The llama is kind of camouflaged in Machu Picchu. So when we try to plot the distribution, here is the colour of every pixel plotted in a red, green, blue three-dimensional space, and you see it doesn't really separate out into foreground and background. And in fact, knowing which pixels came from the foreground and the background and plotting their position in colour space separately, you see again they're sort of rather intertwined. Not hopelessly intertwined, so the job can be done, but still with a lot of ambiguity, so that certain colours could belong to foreground or background. Well, we did this kind of modelling. We used these colour spaces to build colour distribution models for all of the pixels in the foreground and the background, and we built a machine which could do this, and with any luck I may be able to demonstrate the machine to you. Let's see. Okay. Here we are. So here it is, the machine running in Microsoft Office. If you buy any copy of Office, you will find this. It's every Office application of Word has it in, PowerPoint has it in, even Excel has it in. I challenge you to find work out what you're going to do with it in Excel, but you know, I think it must have been easier to put it in than leave it out. And so here we are. We've asked for the foreground, the turtle against its background, and you know, it's pretty much there, but it's not actually perfect. So I pick up the retouching brush here and sort of add a bit of tail. And oh, it got this bit as well, but oh dear, it's picked up a fish, which is actually not part of the tail, the turtle. So I just sort of strike through and now it's gone. So now we separated our foreground and background, and behind the scenes, an optimization computation is going on many times, computing with that generative model, using Bayes' formula to invert the model and infer what is the foreground and the background. And see, now you can have all kinds of fun with it with your end-of-term essay. So many variations on this theme have been built. I particularly love this one, which comes from the University of Oxford, where they did something similar but with movies. And so now what you'll see is this same bag of pixels model, as this particular generative model is often called, run on a movie, separating the head from its background. And you see it really is rather tenacious. The lady is not making any effort to cooperate. She's making life as difficult as possible. You see what's really happening is that she is still and the room is whirling around her head at great speed. Let me talk about another problem, the one that Chris referred to, that we looked at in Microsoft, and this is capturing the whole movement of the body. Supposing you wanted to do this, they want to do this in the movie industry, so when you want to pretend that an actor is actually Gollum, then you want to track the movement of that actor and turn that into simulated movements. And in order to do that, the actor is covered, you see, in these little white dots. These are very special material, retro-reflecting material, a bit like what they put in the number plates of cars. So the light from the camera has a light next to it, is reflected back very efficiently to the camera and appears very bright. And that makes the job a lot easier, as you can imagine. But, building software for the Xbox, of course, they didn't want to insist that before you could play an Xbox game, you had to put this suit on. So we had to solve a harder problem, which was really recognizing the uninstrumented limbs with you wearing just whatever you want to wear. Here's the instrument we were given to do it with, the 3D camera. Here are many synthesized bodies. These are rather strange images. That's because they're coding distance or depth rather than color. So you see how the camera has more than one eye. Its outer two eyes are used like your two eyes to do stereo vision, to tell when things are near and when things are far. And so here are simulated images where black means near and white means far. And we can simulate many of these sort of hypothetical poses of the body. And that can be used to, in principle, to do the analysis. So let me show you this. So what I'm going to show you is how this synthetic approach, the generative model, works. To begin with, it works, but after a while, you'll see something a little unfortunate happening. So here we are. The synthetic model is represented by that yellow skeleton. To make it easy to see, we're showing the skeleton of the body, and the pseudo-color image is the depth map, red for near, I guess, and blue for far. And you see that the synthetic model was following the body quite nicely. But then something went slightly wrong, and now it seems not to be recovering. So seems like this generative approach, synthesizing bodies, what's happening behind the scenes there that you don't see is that many possible bodies are being synthesized until one is found that fits. The one that you see displayed on any video frame is the one that fit best, that best estimator that I mentioned earlier with the Bayes formula. And so that works up to a point, but you see it's not enough on its own. So when the motion is very vigorous, then the hypotheses start exploring the wrong part of the 3D space. And of course, another situation in which that is a real problem is when you first start playing the game. You come into the room, initially the instrument has no idea where you are. It's very likely to be looking in the wrong place. We need to do more to help the 3D camera understand where you are. So at this point, we decided not to throw away the generative model because it seemed powerful, even though it couldn't do everything we wanted, but seemed that using some of the research that Chris referred to earlier to at least get the approximate location of the body in the scene would really help. And my contribution at this point was critical, which was that I told the researchers that were proposing to do this, to use image recognition to solve the problem, that it would never work. And when you tell young scientists that what they're trying to do is simply not going to work, that they try even harder. So that's I wish I could say that that was my tactic all along. But anyway, it really did work. So we needed to generate a lot of data so that we could go back to the black box idea and somehow combine it with the generative idea to make kind of the best of both worlds. And of course, we could generate the data like you just saw. Let me do that again, by having a man wear a coloured suit that is colouring all the different parts of the body so that the images are already labelled. But we really needed a lot of data. Think back to the ImageNet challenge, the 1,000 topics, 1 million images we needed to train that system. And sort of getting 1 million movies sounds like too many. So we were worried about that and didn't think it would work. And we decided to try simulation. And so we generated artificial bodies, just got a kind of combination of real motion capture with computer graphic synthesis to get these artificially labeled bodies. And we knew we would have to make quite a few of them. So here you see there seem to be several dozen of them that we had to use. And, well, more like 100, in fact, or several hundred that we needed before we could, well, probably 1,000 or maybe 10,000. Well, actually, to be honest with you, we needed the full million. We needed the full million before we could capture all of the variability, the different sizes of body, the different shapes of body, all the variations that would occur naturally before we could say, hand on heart, that our black box detector had had a chance to see all of the possibilities. And finally, we were able to couple the two ideas together, the black box detector and the generative model, and build something which kind of works in harmony. And so here you see on the left the detected depth maps, and the next set of frames going across the inferred body parts. So you see they look quite like the synthetic data. That's good. They're not perfect replicas of the synthetic data. You can see a little bit of fizzing, as it were, with the colors, pixels flicking on and off occasionally, but it's not bad. It's quite close to the data that we trained it on. And then finally, using the generative model, we are able to infer the positions of all of the joints of the body. So in the end, I said which would win, the black box detectors or the generative models, it's like a concerto. You know, the soloist and the orchestra begin by arguing but end up in beautiful harmony by putting their strengths together. And since then, a lot more has been done with this technology, and the team at Microsoft Research not very long ago used this for tracking hands in all their detail. And this is really a very hard problem, some ways harder than the body because of the way the fingers can hide themselves behind the palm. And you see, despite that, the accuracy they're getting and the ability to manipulate artificial objects in a gaming world is really very acute. And of course, gaming is a fantastic domain for developing technologies, and we were able to do that, but it's been used in many other places. For example, in medicine, here we have the same non-contact gaming technology used in the operating theatre to manipulate the image that the surgeon sees. The surgeon can't easily go and use the computer, although legend has it that they used to kind of walk up to the computer and put their hands inside the operating gown and try and use the keyboard through the gown, but you know, they're scrubbed up, so really they shouldn't be using the keyboard. And so having a system which uses a combination of gesture and speech to control the view is really very exciting, here being tried out by a surgeon at King's College in London who helped us with this. More recently, another combination of generative and discriminative models, rather like the thing that we built for Office, but now also using discriminative models to learn, in this case, what is where is the fetus in a fetal ultrasound, and to outline that reliably. And on the left, on the right, you see the two frames. You see the purple one is what the computer did, and the red one is what a human expert did. And you see, this is just last year, how incredibly well this is working. Just one last comment I want to make before I finish. You know, Fei-Fei Li, the Stanford professor, said we've reached the smarts of the 3-year-old, now on to 13. That was bold of her, but it makes the point there really is a tremendous amount for us still to do. And thinking about the ImageNet example with 1,000 cases of 1,000 classes with 1,000 images for each class, we've done a lot with big data. But it's rather striking that humans don't seem to need big data to do their learning. So if you imagine asking your 3-year-old, or maybe it's a 2-year-old, I'm not quite calibrated these days, you know, the 2-year-old has seen many cars, let's say, and has had the opportunity to learn very reliably what a car is. And now it sees its first lorry. And how many lorries is it going to need to see before it knows what a lorry is? Maybe 2, maybe 3, certainly not 1,000. We're a very, very long way from understanding how that is done. With our artificial intelligence tools, we would tend to need another 1,000. Of course, people who do research in this area are very aware of this problem and are trying all kinds of things to reduce the amount of data you would need with the lorry. And they're able to reduce perhaps from 1,000 to 100, that kind of thing, but not to get anywhere near the incredible efficiency of the use of data that humans seem to exhibit when they're learning. So that's what I want to end with. In artificial intelligence, we've seen an amazing kind of cycle of technologies coming in and out. Even the popularity of AI itself, we've had many AI winters, so-called, where people kind of lost confidence. AI had perhaps promised too much, and people lost confidence in what AI could deliver. Arguably, the first AI winter was Ada Lovelace herself with her rather downbeat assessment of whether machines would ever really be able to think in an original way. And we've been through many cycles of the use of logic, very early use of neural networks, those black box detectors. That early hope was dashed by some mathematicians from MIT that proved that these black box detectors would never work. And that kind of knocked everybody back for a while before some researchers were brave enough to have a go anyway. They managed to break free of the conditions of the theorem by adding 1 or 2 extra details. and things started working again. And then we had the kind of golden age of generative models and Bayesian reasoning, and for a long while the field of artificial intelligence was rather exclusively involved in that, until the recent big data era of black box classifiers, deep neural networks. And so one can speculate about what are we going to get next, and maybe it will be small data. This is what the 3-year-olds seem to be able to do. They can do inference from small data. How are they going to be able to do it? Well, one idea which I haven't had time to talk about is good old-fashioned logic in AI. There are some amazing demonstrations of the speed with which you can learn from logic. And there's a sort of trade-off there that neural networks are very good at coping with ambiguity and inconsistency in data. Logic is not very tolerant of that, but it seems to have the complementary strength that it can be very efficient with data. Another idea is this idea of simulation that we talked about in the context of generative modeling. And it seems that when you don't have much data, simulating more data that is nonetheless true enough to your task to be usable is going to be very important. So simulation may also be a key. And then finally, this whole idea of generative modeling, for example, the idea that allowed us to discriminate foreground from background when we didn't have big data, generalizing that notion, and people are working very hard on that in many domains and with some fascinating science going on. And this is what's going to power the coming revolution in artificial intelligence, where we begin to have robots which can cooperate with humans, where our transportation systems are transformed. This self-driving car, I hasten to add, is highly experimental. You won't really have all that kit on the roof with the production model. And things like the Amazon Echo, which are able to understand what you're saying and interpret your requests. And you know, if you're having a conversation about a pair of red shoes that you rather admire at the dinner table, before you know where you are, it will have bought them, and by the time dinner is over, a drone will have arrived at the front door with the red shoes. Thank you very much.
Thank you, Andrew, for a super lecture. I would like to let the audience start the discussion. Please, there'll be roving mics. Put your hand up and give your name and affiliation before you ask your question. Are there roving mics? Ah, here we go.
Andrew, fantastic lecture. I have a question about big and small data.
Yes.
The child.
Yes.
The child might only have 2 examples of the lorry,
Yeah.
but it has real-time video streaming into its eyeballs 10 hours a day, or however many hours it's awake.
Yes.
So really it's seeing vast amounts of unlabeled data.
Yes.
Any thoughts on that?
Yes, so I think, you know, I didn't quite get so far as to say this, but I think part of the challenge for AI is to leverage exactly this opportunity, that a small fraction of the data in the world is labelled. And Google gives us a rather skewed idea of the world, because a lot of the data on Google is labelled, or approximately so. But you know, for the child growing up, it sees a tremendous amount of material, and only a small fragment of that is pointed out by its parents. You know, that is a lorry. And beyond that, partly what generative modeling will help to do is to associate pieces of data which are similar, so that the ones that have not been labelled can be associated with the ones that have been labelled, effectively expanding the amount of labelled data that the child has at its fingertips.
Excuse me, are the mics working now? There's a guy there. Yeah, the one putting up his hand. And also there's a guy at the back, you next, so that one, and then.
Hi there.
Who are you and what's your opinion?
Sorry, I'm Andy Bennett. I'm CEO of Register Dynamics. In the No, I'm glad you mentioned that we're going to get another crack at AI, because it looks like now we've got the skills and we've got the experience and we've got the compute power to do it. But lately there seems to have been a whole bunch of people who, really intelligent people who I have a lot of time for, but aren't computer scientists, coming into our industry and stirring things up and saying that the robot uprising is coming and this kind of thing. And I guess that's kind of important when it reaches the kind of the zeitgeist of the normal person. So in the 80s, for example, when I was growing up, there was not as accepted understanding of animal rights as there is now, and normal people took it upon themselves to decide that was important, and they protested and they made it a thing. When do you think we'll see the first AI rights protests, if ever?
Well, I hope that we have got ahead of the curve this time. Actually, the Royal Society is doing a rather good job. Chris just appeared on a panel to celebrate the announcement of their recent report on machine learning technologies, which is paying a lot of attention to how people perceive artificial intelligence and paying a lot of attention to what are the risks and how are we going to deal with artificial intelligence safely. And my sense is that engineers are taking these aspects of artificial intelligence very seriously, both the safety aspects, both the and the effects on society, what's going to happen to the jobs landscape, and I think people are paying a lot of attention to it. I think it's inevitable that when you have a technology like this, which is powerful enough to be really interesting, it's also powerful enough to have serious downsides, like those associated with safety and associated with transforming people's work life. And so I think all I can say is we need to put just as much effort into those aspects of the effect of artificial intelligence on society as we do into the technology itself. And as things appear at the moment, I'd say the signs are good that people are taking that very seriously.
Yorick Wilkes, Oxford Internet Institute. You nicely contrasted the two approaches to machine learning, as it were, top-down and bottom-up. And of course, as you know, this goes back a long way into all parts of AI. And I can remember Gene Charniak in the 90s writing a book on machine learning saying he didn't want black box explanations because, sorry, he didn't want black box methods because they lacked explanation, and he was a scientist. And black box explanations were for engineers who wanted to do things, and he was a scientist and he wanted to understand how the world worked. And this all sounded a bit prissy, but one sort of could see the sort of Royal Society-ish sort of motivation behind it, the idea that somehow the universe must be comprehensible, phenomena must be understandable. And just, as you probably know, I mean, the last few years, DARPA, a major sponsor, has put out calls for proposals as to how to explain black box performance post hoc, to give explanations. It's not quite clear why they want them, but again, it's this mysterious quasi-scientific motivation. What's your comment on that sort of way of looking at it?
Well, I think you're right that it is scientifically interesting to understand what the black box did, but it's also operationally rather important. So if the black box just denied you credit, the bank, it's not going to be very satisfying to the customer to be told, well, sorry, the black box told me. And similarly, if a black box diagnoses a disease, the physician is not going to be very satisfied with having to say, the black box told me. So I think there are going to be lots of reasons, very practical reasons, for thinking very hard about getting black boxes to explain themselves. And this is something which has really caught fire just in the last year or so of research. There's now a lot of research coming out on lots of different ways, actually, that you might approach this. And one way is to build your classifier on generative models, but then maybe you take a hit on performance. So another thing you can do is to take the black box classifier, do a classification with it, and then kind of break the black box open just for the operating regime around the decision that was made. So, you may not hope to be able to explain in any intuitive way what the whole black box did, but it turned out that explaining a particular decision may be a bit more doable. And there are lots of fascinating approaches to this that are happening at the moment, and as you say, I think it's very important.
Hello? Hello, is it on? Can you hear me? Hello, Amit from ADM Software. At this very moment, your software or your concepts such as speech recognition and image recognition,
Yeah.
would that not make it difficult in the online world to make would it make it difficult to distinguish between a human and a computer at this very moment where your technology can be misused or misapplied?
Yeah, for sure. I mean,
So is that
again, it's this idea that any really powerful technology brings benefits and also problems with it. I mean, I don't know if you've been following the technical news, but recently they've just invented a machine that will kind of animate you. I mean, so it just needs to see a bit of video of you talking, saying a few things, and now that you can be synthesized and made to say all kinds of things. And I mean, actually, there have been various generations of this technology over the last few years. Actually, the Chipola group in Cambridge University is one of the pioneers in this, and it's now getting to a kind of rather worrying level where, yes, there is an issue. I don't have a solution there. It's a sort of fascinating problem to be faced with. It's yet one more way in which our computer systems can be attacked.
On its simplest level would be to recognize the capture image or something like that from using one of your technologies.
Yes, I think artificial intelligence has broken captures now, hasn't it,
Yeah.
Chris?
So still, it's widely used in the online world.
Yes.
So that's why I'm. Sorry.
Jim Conboy, Charteridge Scientific. Humans have a concept of a new object that they've never seen before.
Yes.
I don't see how this is addressed by your methodology, and if your driverless car encounters something that fell off the back of a lorry, it could be relevant.
Yes, well, I mean, it may very likely not be able to name the thing that fell off the back of the lorry, but it might avoid running over it. So you don't actually have to recognize it. So, for example, the 3D imaging technology, which is getting very sophisticated, I mean, there are different ways of doing it, even with pairs of cameras, with rotating LiDARs, they call them, sort of a light-driven radar. These are able to build up a 3D map of the world and can easily recognize, for example, when there's a lump in the road, and without knowing what the lump is. So I think we can do something in the face of an unknown object.
So I have a question. You did this object focus of, for example, you have the woman and a cat in the crowd.
Yes.
But previously, at the beginning, you had autonomous vehicles where there was some recognition of a person being a problem person. And is there anything to do with meaning happening at the moment, or is it to come through the AI and logic of the future and the small data?
With meaning?
Yes, with, for example, no, that person is not going to walk across, this person is going to walk across in front. Is there any interpretation, or is it all object focus?
You know, I wouldn't want to say that the system had, was getting meaning out of the scene, but it can certainly learn those kinds of things in a rote kind of fashion. So you might not want to do this experiment, but if you ran a lot of these situations and measured who was knocked down and who wasn't, perhaps we can find a more acceptable way of doing this, then you could register features of the person as they were at the side of the road, look at how that correlates with the outcome, did they survive or did they not, and build, for example, a black box that will predict that.
So at the moment there's this real boundary of what can you do up to that point of not then putting on interpretation.
Yes, I don't know. I think you and I will have to sit down over a glass of wine to see what does it really mean to put an interpretation on the data.
Any more questions? Yes. Good. I didn't want to be last.
Inside Tech. The title of the lecture is Machines That Learn to See.
Yeah.
Now, I wondered if by seeing you also meant observation and perception, because I note that you were moving from seeing and then perception. Were you deliberately using these terms interchangeably? Or they are more precise than that? And if the answer to my question is no, what is the potential of AI eventually developing to a state where they will actually be able to observe and perceive as the word mean?
Yes, so do you think I explained seeing and not observing, or observing and not seeing?
That's the distinction I'm looking for if you were using these ideas interchangeably. So by seeing, did you also mean observing and perceiving? Because we know there are distinctions between them.
Well, I'm not too clear what distinction you have in mind, so a little hard for me to answer. But maybe you can tell us, give us an example of something that would be observing but not seeing.
Well, by observing, we actually making judgment.
Oh, I see, yes.
So we take in whatever it is that we are watching or seeing and make judgment, evaluative judgment. So that is what I will interpret observation to be, rather than just passively seeing and trying.
So I think that's quite like Philippa's question. It's sort of,
thank you.
Did you simply enjoy the richness of what was set before you, or did you base an action on and have an outcome from what you observed? And so we can, by training what's sometimes called end-to-end systems, we can include the action, if you like, so that the perception is followed by an action and that the two are linked by learning. So I think we can do it.
Harin Selheva from University of Buckingham. Very interesting talk, thank you.
Thanks.
So we've reached a 3-year-old and we are working towards a 13-year-old.
Yeah.
How long will it take for us to get to a 23-year-old? And when we get there, what would a computer be capable of doing?
Well, I think many 13-year-olds are sharper than some 23-year-olds, so that might mean going backwards. But getting to 13, I'm not quite sure when we're going to get there. I think part of what's going to be needed is a lot more sophistication with the combination of language and images. So you saw the captioning example. People have just begun to who work on computer vision, to take language seriously. And some low-hanging fruit has been quite evident that there are some things you can make work just by having very shallow models of language associated with the images. So I think the next step will be to be able to use much richer language. So, for example, what you saw on the screen there was very factual statements about the content of the scene, but nothing about, for example, the intentions of people in the scene, or about things that might be present in the scene but are not actually directly visible, but are kind of inferred by their indirect effects. Many more sophisticated levels of language that. And I think that's one area where a lot of progress will be made, but I don't know how fast.
Okay, does anyone have any more questions? Oh, there's one. Oh, there's lots. I'm going to stop it at 8. So the one at the back.
My name is Okoye, and I work for Beam. It's an IT company. So my question is, based on the fact that human beings are limited in their way of thinking, and we are the ones writing the algorithm for the computer to use, so is there a way of creating a system which actually can perfect that algorithm and make it better? I don't know.
Yes, I think so. So I talked a little bit about how effective learning with logic can be. And so one example of that is you can teach a program to take a paragraph with some information in it and make a kind of abbreviated version of that paragraph. So maybe the paragraph talks about you, your name and address, your postcode, your telephone number, but all you wanted was your first initial on the telephone number. So supposing you want to write a program that makes that transformation. What you can do is search over a space of possible programs and automatically monitor the performance of that program until you get the one that does the job perfectly. So that, if you like, is I don't know if that sort of matches what you had in mind, but that's an example of the computer taking simple programs, admittedly, and refining them. But of course there are lots of other more conventional ways in which computers refine programs anyway, like automatic compiler optimization, I guess, is a kind of optimization inside the inside the computer where it's fiddling about with your program to make it work as well as possible. For example, taking loops and unrolling them, various transformations that it can make to the program to make it work better.
There was a gaggle of about 3 in the middle there. Who wants to put up their hands? Oh, you're not in the middle. Mike, what you can do. Mike. Last one there.
Michael Form.
We heard you.
Oh, good. Michael Foreman, also from the University of Edinburgh School of Informatics. Thank you, Andrew. Wonderful talk. You've talked about vision, and it's great because we can see what you mean with your examples. But what's the scope for taking these kinds of techniques and applying them to things we can't do, like echolocation, like bats, or whatever dolphins do, and so forth, applying them in other domains and giving us powers we wouldn't otherwise have access to?
Yeah, I mean, we can definitely do it. I mean, it's at least we can definitely try to do it. The echoes that come back from bats are signals of a kind, and the science of signal processing is not very far from image processing, and many of the techniques that are used are in common. And of course, because a signal is not visible, I mean, infrared is an example. We don't see infrared images with our naked eyes, but the data is there and gathered by satellites that are traveling above us at this very moment, gathering huge quantities of infrared data from the Earth. And of course, we can use techniques really quite similar to the ones that I've described to analyze that data.
There was one here, if we can make that the last one. Somebody can give a mic to the one here. Thank you.
It's thunder.
How do you? My name is Mr. Martin. I'm retired. Actually, I'm age 78. I've recently been in hospital right now. You're talking about speech, but there are other means of communication, like, for example, voice or noise, of course. And there is touch, for example, where I was in the hospital. A consultant very carefully touched certain parts of my body to make certain whether I was well or not. And surely your methods could also be used, therefore, for other uses apart from just from speech.
So I'm not quite sure what you have in mind. You're thinking of a robot with fingers that palpates you.
Yes, you might do that. Yes, he was doing something like that as he was examining my stomach, actually. Yeah. But again, that is certainly a medical interest. And of course, he will be very experienced. He does detect, therefore, certain behaviour that I might not really like to have very much. But it doesn't really cause speech, I know, but it is very valuable. That would be the point.
Well, I think we're going to see a lot more robots in the in hospitals. There's already the very well-known Da Vinci robot, which is really a kind of a puppet that you operate remotely, but it makes very precise actions and is used very commonly for certain kinds of operations. But that's still human operated. There's a lot of research going on taking robots like that and making them autonomous. So Imperial College's Hamlin Centre, for example, is famous for this work of making those robots more and more automatic. I think what they do at the moment is they do procedures. I haven't heard of one actually feeling its way around your body, but there are a lot of people working on tactile sensors, and so yes, I hadn't thought of that, but that's an interesting idea, and I guess that could happen.
Thank you, Andrew.
Thanks.
And thank you, everybody, for an interesting discussion. Now I'd like to ask Mark Girolami from Imperial College London and Director of the Lloyd's Register Foundation, a programme associated with the Alan Turing Institute, to give the vote of thanks.
So this has been an absolutely wonderful evening so far. That was a very stimulating question and answer session, and following on from a quite superb presentation by Andrew. So I'm really the last hurdle between you and the drinks and the buffet and carrying on discussion about this particular lecture. So I'll keep it brief, and I was actually told to keep it brief. So it was a really lovely series of talks introduced by Sir Tim, who is the principal of the University of Edinburgh, followed by Chris, who is a graduate from the University of Edinburgh doing his PhD under Peter Higgs, and of course is also a professor at the University of Edinburgh. And then we followed on with Andrew, who worked in Edinburgh at Ferranti and then did his PhD under Donald Meachie at the University of Edinburgh. And then we saw another notable alumni from the University of Edinburgh in Andrew's talk, Thomas Bayes. So it probably comes as no surprise to many of you that from my accent, I don't come from Edinburgh. So it's quite gratifying that they had to pull a man in from the University of Glasgow, a graduate from the University of Glasgow, to give the vote of thanks and to end the evening. So what can I say about Andrew's contributions? I only really met Andrew a couple of years ago. Of course, the longa manus of his work was extremely well known to me. And I got to know Andrew when he was the director of the Alan Turing Institute, and we both went through the rough and tumble and the boisterous activity that's required to really bootstrap a national institute from nothing. And I'm really grateful to Andrew for being such a gentleman and very kind and gracious, and certainly to me. And it reminds me when Andrew suggested that I might be interested in taking this job on, he asked me to write a proposal as to what my vision would be and so forth. And when I handed it to him, one of the first things he said was, "This will never work." But now I understand that he wasn't being a grumpy old man, that he was actually trying to push me forward in so many ways. The difference between empirical detectors and generative models is one that certainly very recently has generated an awful lot of interest and renewed interest in AI and so forth. And one of the questions that was asked was about the ability of these black boxes to explain their decisions or explain how they've come to these decisions. And can we actually understand what it is that they do? And the fact is that we don't understand what they do. But that shouldn't in any way inhibit us from embracing them and trying to understand them. Let's just remember that the Clay Institute has as one of its challenges defining a proof of Navier-Stokes equations, which have been around for 200 years and have been used for 200 years to understand fluid flow, to help design aerofoils in aircraft and propellers and ships, and of course drive our weather forecasting systems. So if it hasn't inhibited us not knowing that there is a proof of the existence of solutions of particular regularity and smoothness of Navier-Stokes equations, and 200 years later we still don't have that proof, it may well be another couple of centuries before we really have a deep understanding of empirical detectors, but it certainly should not inhibit us from continuing to exploit them and to use them for the sort of fantastic applications and uses that we heard Andrew talking about. So I'd like to just say thank you very much to Tim and to Chris and to the start of the show, to Andrew for a fantastic evening so far, and looking forward to some wine-lubricated discussion and argument next door later on. So thank you.
So thank you, Mark. Thank you for the star of the show, Andrew, and the other charming, grounded people. Now, all I have to do is say, welcome to the reception. This is free due to the BCS 60th anniversary, and so thank you to BCS for supporting this event tonight.